Okay, in 11.1 we're going to talk about what is an exponential function. And so let's just start with that. Let's leave an exponential function. So this is a function, so I'm going to write it as f of x equals b, so some number raised to the x power. So in this case our variable is actually in the exponent. This is the first time we've had that. And a couple of things. X is a real number. Just going to abbreviate here a little bit. B has to be greater than 0, and it can't equal 1. And the reason it can't equal 1 is what's 1 raised to any power? It's 1. That's not an exponential function. That's just a straight line, horizontal line. So exponential functions model rapid growth. So I should say rapid increase or decrease, because it could be increasing rapidly or decreasing rapidly. Okay, so unlike chapter 3, which is linear growth, which occurs at a steady rate, this is rapid increase. So this could be population, this could be bacteria, that's increasing at a much faster rate. It's not linear. Okay, so let's evaluate some exponential functions. I have f of x equals 3 to the x. Find f of 1.5, and that just means plug in 1.5 for x and then use your calculator. 3 raised to the 1.5 power, and you should get 5.2. For 2, it says the population in Nevada is modeled by this equation, where t is the number of years since 1990. So this is our starting year, and we count from there. So what was the population? Oops, that shouldn't be there. In 2010. So 2010 is 20 years later. So I want to find my population 20 years later. So I'm going to plug in that for t. And then again, just put this into your calculator all at once. 6,191 times 1.04 raised to the 20th power. And you should get, since it's people, I'm going to round to the nearest whole number, 13,565 people. And the last one says in 1965, the federal debt was $322.3 billion. During the next 30 years, it increased by about 10.2% per year. This is modeled by this equation, where t is the number of years after 1965. About how much was the federal debt in 1970? So 1970 is 5 years later, so that means I'm plugging in 5 for t. And then again, just use your calculator. Plug this into your calculator. 3.22.3 times 1.102 raised to the 5th power, and you should get, don't forget your units here, $523.8 billion. Okay, a natural exponential function is represented with the letter e. So just like we have pi, which is a number, 3.14 repeating, e is also a number. And you can actually find this on your calculator. Look for the button on your calculator that says e to the x. And when you type that in, when you say e and it says raise it to a power, just type in 1. So raise it to the first power, and you should get the number 2.718. That is what e equals. Okay. So it's just a number represented by the letter e, just like we have pi representing 3.14. Okay, so let's look at using this exponential function. This is used for continuous growth. For example, if you have money that's continuously growing, if you have bacteria or cells growing continuously, that's where e comes in. So we're going to have, this is hard to see, e to the x minus 2, and we want to find f of 4. So that means plug in 4 for x, and you could put it into your calculator just like this, or you could simplify your exponent first. This is saying what's e squared. Go ahead. Actually, that minus 2 is not supposed to be in the exponent. So that's fine. We'll go ahead and put this in, but I need to get my calculator. So we're going to do e squared. So I'm just going to use this calculator right here. So I'm going to take e, 2.718, and I'm going to raise it to the second power, and I'm going to round to 2 decimal places, 7.39. So I get approximately 7.39. Right, the growth rate of E. coli is given by this formula, okay, where T is the time in minutes and Q is the number of cells. How many cells are there after 60 minutes? So this is continuous growth, and I want to know in basically 1 hour, how many cells do I have? This 100 actually tells me that's what I started with, so it'll be interesting to see what we have after 1 hour. So you plug in 60 and put this in, 100, E raised to them. Make sure you put the 0.035 times 60 in parentheses to show your calculator that all of that's raised to that power. Or you could do this multiplication first, then you don't have to worry about all those parentheses. And when you plug that in, you get 816.6. Let's round to a whole cell. So about 817 cells. All right, we're going to graph exponential functions. I'm going to graph 3 to the x and 5 to the x. So when I come here, I'm going to raise 3 to the x power and graph that. You see here I have an exponential growth, and I'm going to label a couple things on this before I graph the other one. So 3 to the x, this point right here where it hits the y-axis, whoops, is 0. And let's just think about this. If I plug in 0 for x, 3 to the 0 power is what? And that's 1. So this is the 0.01. So unless you add, subtract, multiply this exponential by something outside of this, it will always go through the 0.01 because anything raised to the 0 power is 1. Okay, it's getting closer and closer to this x-axis here, but it will actually never cross it, and that's because 3 raised to a power can never be a negative number. This just gets to be smaller and smaller fractions, so it's getting closer to that line, but it won't ever cross over it. Okay, and that's modeling rapid growth here. So this is increasing with time, you could say. Okay, let's write the domain for this graph. The domain, there's no breaks in this graph. It continues on, so it's all real numbers or negative infinity to infinity. And then for the range, if you start at negative infinity and work your way up, your y values start out right after 0. So remember, it can't equal 0 because 3 raised to any power will never be 0, but it's just greater than it. So y is greater than 0. Okay, so now let's graph 5 raised to the x power. And that's in green. And what I want you to notice is it still goes through the 0.01, and it still has the same domain and range. The difference here for the 5 to the x is that it's just a little steeper. So this 3 to the x, this is increasing 3-fold, right? And then the 5 to the x is increasing 5-fold, so it's just increasing at a steeper rate. And that's really the only difference of the basic exponentials, if we're not doing anything else to them, is that how fast is it increasing or decreasing. So this is a little closer to the y-axis, and that's really the only difference in those two graphs. Okay, so let's do the same thing graph, except 1/3 x. So instead of a whole number, so I'm going to clear these. And I'm going to make sure you put your 1/3 in parentheses to show all of that is raised to this power. I'm going to go ahead and graph it. And so you're going to notice a couple of things, that this is modeling instead of an increase in growth, it's modeling a decrease. So over time, things are decreasing. It's still getting closer and closer to the x-axis, but never crossing. It still goes through the point right here, 0, 1. It still has the same domain and range even though it's decreasing. Okay, y is still greater than 0 and you still have all real numbers for your x values. The only thing that's different is it's modeling a decrease. Okay, so how do we solve exponential equations of the form b to the x equals b to the y? Well, you use the fact that if you're saying b raised to some power equals b raised to another power, so the bases here are the same, b and b, the only way that's possible is if these exponents are equal to each other. So the only way b to the x can equal b to the y is if x equals y. Okay, so let's practice solving some problems like this. Okay, so for the first example, we have 4 to the x equals 64. In order to solve this, I want to get the same base. So you start with the smallest number you have, 4, and you say, can 64 be written as 4 raised to a power? And it can. It's 4 raised to the third power is 64. Now that I have the same base, I have 4 and 4, all I need to look at is my exponents. So the only way this is true is if x equals 3. And then I don't have anything to solve here. Sometimes you will, but in this case I don't. So that's just, I'm done. That's my answer. So let's do the same thing with b. My smallest number is 2. So I'm going to rewrite 32 as, or see if I can, which I can in this case. 2 raised to what power is 32, and that's 5. Again, now that I have the same base, all I need to do is look at my exponents. So the only way these are equal is if x equals 5. And again, there's nothing else to solve there. Okay, so let's try this other one. 9 raised to x plus 1 equals 27. So you start with the smallest number, 9, and 27 cannot be written as 9 raised to a power. So in this case, you have to change both the 9 and the 27. And what they both have in common is 3. So I'm going to rewrite 9 as 3 squared, and that's raised to the x plus 1 power, equals 27 is 3 cubed. And now in this case, I can look at these exponents. And remember, when you have a power raised to a power, you're multiplying. So this is 2 times x plus 1 equals 3. And now I do have just a little bit I need to solve. So here I'm going to distribute 2. So I get 2x plus 2 equals 3. Subtract 2 from, whoops. Subtract 2 from both sides. And we're going to get 2x equals 1. Divide both sides by 2. And I get x equals 1/2. Okay, let's do the same thing with b. 5 to the 3x equals 1 over 25. If you don't know what to do right away, let's just start with that 25 and not worry about the fraction right now. So my smallest number is 5. Can 25 be written? Yes, it can be written as 5 squared. Now the problem is I can't have this in the denominator, I need it in the numerator, so this uses a rule of exponents, which says to move this up, you make that 2 negative, so 5 to the negative 2. So usually we're trying to get rid of the negative sign. In this case we're doing the opposite, we're making it negative so I can move it to the numerator. Now that I have the same base, I can set my exponents equal to each other, and so 3x equals negative 2. Divide both sides by 3, x equals negative 2/3. Okay, and one thing I want to mention when we get to logs soon is the reason we have logs. So all of these we've been able to solve, but let's say I had 5 to the x equals 3 to, just equals 3. Let's leave it like that. Okay, so I'm trying to see 5 raised to what power equals 3. There's no common base here. There's no way I can make these have the same base. And so the only way to solve this is by using logs. Okay, so let's look at a finance problem. It says when you deposit money in an account earning interest more than once a year, so for example, a car loan, you have your interest compounded every month, a mortgage payment every month, credit card could be every day. In this case, this is money where you're gaining interest, not paying interest. Use this formula right here to find the amount of money you've earned after a certain amount of time. If your parents deposited $10,000 into an account 18 years ago with an interest rate of 8%, compounded monthly, how much money do you have in this account now? So I'm going to highlight all these amounts. You had $10,000 18 years ago at 8% compounded monthly. Okay, so I'm going to label what these stand for. A is the amount of money you'll have. P is your principal. R is your interest rate. Remember, you have to write that as a decimal. N is the number of times your interest is compounded. So is it compounded monthly? Is it compounded quarterly? So 4 times a year, semi-annually, twice a year. So you just have to see what that says in the problem. And T is the number of years that you're putting it in the account. Okay, and then let's just write down. We don't know the amount. That's what we're trying to find. Our principal is $10,000. Our rate is 0.08. Compounded monthly means it's compounded 12 times a year for a total of 18 years. So I'm going to plug in all these values into our formula. So I get A equals 10,000 1 plus 0.08 divided by 12 raised to the 12 times 18 power. Okay. So you can put this in your calculator all at once. One thing that does help is to actually make maybe the exponent one number. So I'm going to just do the 12 times 18. If you get 216. And so what you can do, whoops, let me fix that. Right. Is instead of having to put this, you have to use a lot of parentheses before and after it. I'm going to just say it was 216. Just plug it in like that. So it's 10,000 parentheses 1 plus 0.08 divided by 12 raised to the 216th power. And then this is money, so use a dollar sign. Okay, and when you plug this in, you should get 42,000. $5 and round to the nearest cent, 74 cents as your answer.